When we talk about the electrophiles in SN2 reactions, we also have to consider the leaving group and the nature of that leaving group. In this case, we're comparing two electrophiles that have that same alkyl group. So we have a primary alkyl halide in both cases because we have one carbon-containing group attached to the alpha carbon. If we want, we can go in and label that alpha carbon. In each of these cases, that's the carbon that's going to be attacked. We have only one carbon attached to each of them, in addition to the leaving group, and then having two H's attached. So we're dealing with the same structure here. The difference for these electrophiles is that leaving group itself. So we have a chlorine versus an iodine. So we're going to use that same common nucleophile that we used in the previous video. We're going to now even have the same alpha carbon structure. So we have that same group coming off. What we're changing is the far right side of this transition state. That halogen is going to change. So the partial charges stay the same because we're dealing with the same kind of neutral as they begin. These leaving groups are going to start to get that developing negative charge as they are kicked off by that nucleophile coming in. They're going to start taking the electrons in their bond and starting to stabilize them right in that transition state. And so we have to think about which one is going to be better at stabilizing that charge. And so just like we talked about with our acid-base chemistry, we saw that atoms that are in the same column, size is really important for them. And chlorine and iodine are in the same column of the periodic table. And iodine is larger than chlorine because it's below chlorine on the periodic table. And so iodine is larger than chlorine. That's going to mean that it will be able to stabilize a negative charge better, and that translates directly to it's also going to be able to stabilize that developing negative charge or partial negative charge, delta minus. It's going to be able to stabilize that better as well. So the iodine can stabilize that developing negative charge in the transition state. It's going to be better at stabilizing that because it's a larger atom. There's more room for that charge to spread out as it starts to develop on that atom. So that's going to mean that we're going to have that transition state being more stable, which is lower in energy. That means we're going to have, for that reaction, lower activation energy or a faster reaction. That's going to mean that that electrophile is going to be better. So that's going to be our better electrophile. Let's take a look at what that looks like on a reaction coordinate diagram. In this diagram, we have in blue our better electrophile. It's kind of the theme for all of these. We've kind of done the better one in blue. This is going to give us, with the iodine stabilizing that delta minus better in the transition state, it's going to make that transition state lower in energy. So that means it's going to have that lower activation energy. It's going to be a faster reaction with the electrophile with that iodine as that leaving group. We would also say since it's a better electrophile for SN2, we'd also say that that leaving group is a better leaving group. So we'd say iodine is a better leaving group than chlorine. And what this comes down to is what that leaving group is supposed to do. So a few things that the leaving group is supposed to do. It's supposed to polarize that alpha carbon. So basically that means it's supposed to make that alpha carbon delta plus. So when we're talking about halogens, we're pulling electron density away from that alpha carbon. That's only part of its job. Its other part of its job is to stabilize that electron density as it starts to be dumped onto it when that alpha carbon leaving group bond breaks in that transition state. So as that nucleophile is coming in for the attack, the bond between the alpha carbon and leaving group starting to break, starting to dump its electron density onto that leaving group, the atom of that leaving group specifically. So in here, as that nucleophile attacks, that bond breaks. As this atom starts to develop that negative charge, that atom has to be able to stabilize that negative charge and that developing delta minus in that transition state. So basically, from when the attack happens in that transition state and onward, we're going to have to be able to have that atom being able to stabilize that negative charge or that developing negative charge or charge or electrons from that alpha carbon leaving group bond. It's going to have to stabilize it. So let's see, what are atoms that kind of are able to stabilize that charge very well? So we have our halogens that we've seen a lot of, iodine, bromine, chlorine. These are relatively large atoms on the periodic table. They're relatively good at stabilizing this negative charge as it's developing that transition state. So we're going to see that compared to some other atoms, these are going to have among the lower energy transition states. So we're going to have faster EAs, faster reactions with these groups as leaving groups. So when they leave, they're going to be I minus, Br minus, and Cl minus. Fluorine is actually too small. So it's actually in that same row of the periodic table as oxygen, carbon, nitrogen. Second row, we're not going to see, unless there's something else helping out this atom, we're not going to see those as leaving groups. So we're not going to see an OH as a leaving group. That's a terrible leaving group for SN2 reactions. We saw that leave like oxygens that were negatively charged. We saw them leaving in other reactions that we were dealing with before under basic conditions, more specifically. When the push and when they're being kicked off of the molecule from something within the same molecule, that's a different story versus the ones that are actually being pushed off from a different atom, a nucleophile coming in. So for SN2 reactions, those second row elements are going to be really bad leaving groups unless there's something else going on to help stabilize them. So fluorine is going to be really bad along with everything else in that second row. But one of the things that we can have is, so if we do have an oxygen as a leaving group, we do have to have something else that's beside it that's able to stabilize it. So we can take, for example, things like OH groups, and we can actually make them into better leaving groups by transforming them into something that's sulfur containing, or by, in some cases, protonating an OH to make an OH2 group. So those are some ways that we can still have an oxygen be a part of a leaving group, but OH itself is not going to be a good leaving group, or OCH3 itself, like that's not going to be a good leaving group because you need to be able to help out that oxygen. So in the sulfur containing leaving groups, we have resonance possible with these pi bonds that are next to it. So we have our mesylate group. This is abbreviated as MS. And so typically on our electrophile, we'd see our alpha carbon attached to an OMS group. That would be a good leaving group because this MS stands for this, which is actually able to resonance stabilize this oxygen. Same thing for the tosylate group. We have that resonance stabilization, and it's abbreviated as OTS when it's attached to the alpha carbon. For our triflate, we also have that resonance stabilization. We have some induction as well from the CF3 group. So this is actually one of the really, really good leaving groups we can convert oxygen into. This is called triflate. And so we would see OTF as what is abbreviated on that oxygen. So the alpha carbon would be attached to an OTF group. That's a good leaving group. So when the oxygen's in those forms, they're good. If it was an OH, bad leaving group. OCH3, bad leaving group. Any other oxygen alkyl type chain, bad leaving group unless there's some resonance in there. So these are examples. These are 3 examples to know for good leaving groups involving oxygen. We also, if we can convert that OH to an OH2, it would be positive on the alpha carbon. That's really going to pull on that alpha carbon. It's also going to be able to stabilize the electron density once it leaves and forms the water after that nucleophile attacks. And so that's going to be a nice neutral leaving group. They don't even have to worry about stabilizing a negative charge because they're just becoming neutral. And so they're really good at leaving. And we have nitrogen versions of the same thing as well. So a lot of variety here in what that electrophile can look like in terms of the electrophile structure around the alpha carbon, in terms of what that leaving group is going to be on that electrophile. So a lot more variation than our carbonyl electrophiles that we were seeing in previous videos. But this does follow a pattern. We do have a lot of examples to keep in mind, but they are going to all be good electrophiles if we have one of these types of leaving groups attached to them.